Alright, now this is the second lecture and we're about to look at differential equations in one dimension and how to solve these using the Galerkin method. So this is where it starts for real. Before we talk about how to solve differential equations with the Galerkin method, we need to talk about what differential equations are. And most useful for that is to look at a model problem, which is a typical problem that we deal with. And since we are, everything around us is made up out of differential equations. So which one should we look at? Well, as design engineers, we're interested in solid mechanics. So let's look at elasticity. So that's what we're going to do now, and later we are also going to look at the heat equation, which is a simpler differential equation. Yeah, we will be looking at more general differential equations later and how to solve them using Galerkin, because these equations that we're going to look at now are pretty simple. Yeah, so Galerkin can solve much more advanced equations of not just second order but higher order as well, and they don't need to be linear. We're going to look at linear equations now, but we can also solve non-linear stuff. It's just that the methods are going to be different, and really that's a different course. And also we are going to look at steady state problems. That means no time is involved. We're looking at stuff that is in equilibrium, and which is stationary, or you might say static, under static load. Okay, so this model problem, this will be a second order differential equation, and it's modeling an elastic rod. So if you look at this, there is a rod that is it's clamped to the ceiling, so that this load here, which is per unit length, sort of makes sense. Like this is your typical weight force, right? So you have f of x, which is the density times the gravitational acceleration, right? And if you integrate this, you will of course get the total weight times the mass times the gravitational acceleration, which is usually what we call the weight force. But next to this, we also have an external load which is placed at the end of this rod, and the coordinate system x is defined to start here, and the length is L. The cross-sectional area of this rod is also known, and it's A. So let's look at this by doing a okay, so now let's look at this by doing a free body diagram. First we will start by making a cut at some arbitrary length L. So this cut at an arbitrary x is going to yield a small section like so, and we have here the normal force, and over here we also have a normal force, and this normal force here is at x, and this one here is at x plus whatever the length of this small piece is, and I'm going to call that delta x. So the length of this is delta x. And of course, because this force that we have here is per unit length, then of course this force here will be F. Alright, now this equilibrium will give us the following. We create an equilibrium equation. So equilibrium will give us, in this direction, we have n of x plus delta x minus n of x, and then we have plus whatever this force is, and we have to integrate over the whole region. So we do the integral, and we integrate from x to x plus delta x, and then we have f, and we do a variable substitution here, f of xc dxc, just something else than x, right? And all of this is of course 0 because this is stationary, there's no acceleration in here. Alright, so let's take a look at this integral business first. So if you take up all of these small sections, and if we consider that they are pretty small, then we can say that, alright, this is some delta x times a arbitrary force along that x. Like if f is linear enough, then this is not too big. Or if the region delta x is very small, then you can say that, all right, x bar here is quite small. So this is valid, of course, for small, or x bar between x and x plus delta x, right? So this is valid all the time. All right, and we'll get back to this, but this is how we define it currently. Like, of course, if delta x is quite big, then f here will be also f of x bar will be quite big and unpredictable, so we need to manage this size a little bit. But this is how we just define this, and then we'll deal with this very soon. Now, note that n of L is equal to f. That's where the boundary condition comes in. So just put that somewhere in the back of your mind. Alright, so what do we do with this stuff? Well, we let now delta x tend towards 0 in the limit. Thus we get, and what do we get from this? Well, we get that the negative derivative of the normal force with respect to x is equal to f. This is what we get. Alright, so what am I doing here? Well, basically, if we do the limit, if we do this limit, then what do we get? We take this here and this, and we divide that by delta x. And this also here is, if the limit goes towards delta x, then we're just looking at a pointwise force, which means that this here goes back to being just f of x. So n of x plus delta x minus n of x, right, over delta x. So this thing is dn dx. So this, I should say, yeah, in the limit this is dn dx. Okay, and then on the other side of the equal sign we have this integral, and as I told you, if delta x goes towards 0, then we just go back to looking at a point region, which is just f of x. So then dn dx plus f is equal to 0. And if we just flip things around to have f on the proper side, then we have dn dx minus dn dx is equal to f. And that's how we want it. Right, so that's our equilibrium equation for the derivative of the forces. Okay, then we have a relation between forces and stresses, which shouldn't be too surprising. Relation. So we have that the normal force is the normal stress times the cross-sectional area on average. Right. So that's our equilibrium rule. And then we have linear elasticity. We have a linear material. So linear, and for that we have a model called Hooke's law, which gives us a constitutive relation, saying that the normal stress is equal to the Young's modulus times the strain. Alright, so this is equilibrium over here, and this is a constitutive relation. And these are relations. And we have another one. Now, what we are assuming, we assume small strain. We assume that we have small strains. What does this mean? Well, if you take a look at the displacements up here, so this thing will be displaced a little bit, like so. And this displacement here, we can call u of x, or in total just u. And the thing is, if you go back and look at this geometric relation, then we have the same thing. We have, let's make a drawing here. We have u of x plus delta x, and we have u of x. So at some point, somewhere in this whole rod, we're looking again at an arbitrary x, and this is a deformed rod. So let's do it like this. Let's copy the whole thing. Alright, so this is the original undeformed one, and then right next to it we will draw the deformed one. So this one is now deformed, and the total deformation is u. But somewhere inside, for instance here, we have a deformation u of x, and then here we have u of x plus delta x, like so. I'm gonna move this to the left and get rid of this stuff because we're just looking at the geometry. Alright, so from this we get the following. I'm going to do this in blue because that's the derivation, and then I will show you the whole end result in black. So we have u of x plus delta x minus u of x, and this is basically the delta, let's call it like so. This is how much we are deforming this this rod. And again, if we do the limit, if we go into the limit, delta x tends towards 0, we will get u of x plus delta x minus u of x over delta x, and this will be something we called epsilon, which is the strain, and it's basically du dx. And this is a geometric relation. So we have this relation as well. So the strain is du dx. Alright, and this is again assuming we have small strains. Usually this is true when the overall deformation is in the region of a couple of percent of the total length. And if it's larger than that, then of course this doesn't really hold. Alright, now combine this. So finally we arrive at, if you combine all of this, we have d dx of EA times du dx, and this is equal to f. So this is our differential equation for x in 0 to L, and this is our differential equation. And then we have a boundary condition. We know that the displacement u at x is equal to 0, that is 0 because of this here. This means u of 0 is 0. And we don't know the displacement at the end, but what we know at the end is, of course, that we have this force. We have this force here at the end. And we know that n of L is equal to F. And we know what n is. So if we combine that, we get EA du dx of L equal to F, right? Because EA du dx of L is the normal force at L, which is F. It's given by F. So this is what we know. And this is where we stop our derivation of our model problem. So this thing is of course only taking tension into account, and basically nothing else. So it's one-dimensional, it's only tension, yeah. And the two material, or this is even just considering one material parameter, which is E, which is the Young modulus. So yeah, so this is the simplest differential equation from solid mechanics. There's one simpler, but that's the heat equation. So again, steady state, there's no time involved. This is linear. We are assuming that the material is linear and that the strains are linear and that we are in equilibrium. So static problem. Alright, so now that we have derived this, we can take a look at the Galerkin's method applied on a differential equation. And we can start with this differential equation. So Galerkin's method, rather, applied on a differential equation in 1D. So we start with the approximation of u of x. So u of x is approximated by capital U of x, which is u1 phi 1 plus u2 phi 2 plus and so on until ui phi I. And again, this is a sum, I is equal to 1 until n ui phi I. And phi I is a function of x. So that's how the that's how the dependency on x comes in. Now, we define a residual, but the residual this time is a residual in force. So define a residual using the differential equation. So we define r of x to be f plus, because we're looking at this, so f plus, and so basically we're moving this here, we move that over to this side, and we set that to not be equal to 0. So f plus d dx of EA times du dx. So this stuff is now not equal to 0. That's our first equation. Okay, and what we're going to do now is do the same thing. We're going to find these coefficients here by just treating this as if it was equal to 0. So basically the same recipe as the other one. So the details look like this. We will find, and really what we're saying here is find the nodal solutions by multiplying 1 with phi I and integrating over the domain. Or I should say over a domain, because we can choose the domain. It doesn't need to be the whole domain. So this means we are integrating, and now I'm integrating from 0 to L, but in general I can integrate, I can make the integral boundaries be anything within 0 to L. So I'm gonna do r of x times phi I of x dx, and I'm gonna set this to 0 for I equal to 1, 2, and so on until n, depending on how high order approximation order I have. So we will get n equations, and let's take a look at these equations. Right, so what are we going to do now is that we take this, we go back to this way of writing it. So we have the differential equation on the left hand side and f on the right hand side, and the integral there. So this is going to be minus 0 to L, and I have d dx EA du dx dx. No, I need to multiply by phi I times phi I dx. This is going to be equal the integral from 0 to L f times phi I dx, and again I is equal to 1 n. Alright, so this is it. It pretty much looks like before. It's just that we have sort of split this integral into two pieces and have not just 0 on the right hand side, but yeah, we move stuff around a little bit, and that's for practical reasons, which we shall get into soon. All right, so we will see this. There's certain questions around this, right? We have this differential of a differential. That's one issue. How do we treat that? We'll get to that. But also, there's nothing here about the rest of it. Like, where do we get in these things, the boundary conditions, right? Because we have a second order differential equation, and that can't be solved by not utilizing this. So we need to use that as well, and that's handled by integration by parts. So I'm gonna recall how you do integration by parts. Integration by parts. So recall that a function d dx differential of two functions u and v, product of two functions like this, can be split, right? This is the product rule. So you have du dx, so you have the derivative of u multiplying the function v plus the derivative of v dx multiplying the function u. Okay, now what you do with this is you just attach, you take this concept and you just attach integrals to this in front of all of these terms. So you have the integral here, d dx of uv dx, and this is equal to integral du dx v dx plus integral dv dx u dx. So we just attached integrals to this, and now we can move stuff around, but this is basically the recipe. You don't need to remember anything than this. You have the product rule, you attach integrals to this, and then you see what do you have and how can you move stuff around to be more practical. Okay, so we make a variable substitution here just to make life easier. So this u here, we will use this recipe, and we're just going to replace this u here by what we have here. So we're going to say that, all right, set u to be equal to ea du dx, and then just utilize this recipe. Okay, so let's start. We have the integral, and I'm not gonna use the just for practical reasons, I'm not gonna use the bounds here in this integral, just to make stuff a little bit more cleaner. Alright, so we have, so in your head, remember, I'm gonna make this in a different color because we're not really doing this, we're just sort of thinking about doing this. So yeah, so we have set u to this, and then we are just following this recipe here. Okay, so we have what? We have du dx, or rather dx of u, which is ea du dx. Right, so I'm gonna make it like this in blue. So this is our u, and then our v here is going to be what? Well, really, we're going to leave v just to make things more general, and I'll get back to this, why we have v here instead of phi, like so, and then just do dx. Okay, and then this is going to be what? Well, this here. So now we have du dx, so that's again integral d dx, and then we have u, which is ea times du dx, right? And then inside of, no, outside of this, we multiply with v and then dx, plus over here we have dv dx times u. So we can start with the u first, right? Because that's ea times du dx. Okay, that's u, and then the derivative of v, and that's just dv dx. And we'll get back to this later. And substitute v. Okay, dx. Good. So that's the first step of doing this stuff. Now we can take a look at what we have. Okay, so if we take a look at this first term here, Well, this is an integral over a derivative, right? So this sort of cancels out, and we can write this in a different way. We can write it like this, because now we need our bounds. So EA du dv, du dx times v, right? And this is we attach our bounds to this, because what we're doing here basically is that this is now just, come on, this stuff here is our u and this is v. So we're doing this. We're going from, let's keep it more general and a little bit more clean. So this is u and we have v, and we're going from a to b here. In general, this is what we're doing. Okay, this is equal to, and then over here we still have the same stuff. So this is just the integral d dx of ea du dx. Wait. No, this is wrong. Hold on. Here I made a mistake. No, I didn't. Yeah, no. Okay, good. Never mind. Cut that. Use take two. D dx ea du dx times v dx, and plus we have ea du dx dv dx. Alright, so this is our starting point now. Alright, so what is sort of unknown here? Or how do we want to arrange this now? Well, if you take a look at this, this is a nasty thing, right? You have the dx here, and then it's a second order differential in here. So we want to move that out, and then this stuff here is very straightforward, because if you look at it, this is just a boundary, right? So we're gonna move this back here. This is your boundary conditions basically, because you have two bounds here, and then all of this is known. So you move that over and you move that to this side. So we will end up with the integral of d dx of ea du dx times v dx equal to this term here, the integral of ea du dx dv dx dx, and then minus ea du dx times v from 0 to L. And now we could expand this just to show what is. So we have ea du dx here of the upper term, which is of L, times v of L, and that's minus EL. And so I'm gonna put big parentheses over this. ea du dx of 0 and v of 0. So this is what we have here, and these are boundary conditions. And really, v here, it's our basis function. So later when we replace it with a basis function, and this basis function, if it's evaluated at L, it's going to evaluate to 1 because it's our right bound, and this thing here is going to evaluate to 1 if it's its own basis function. Otherwise it's going to be evaluated to 0, and we'll see that when we start evaluating this stuff later. But so these v's are going to be handled, and then these other guys here, they are known. So this is known, and well, this is an unknown, but we will be able to compute it later when we have our thing. But it doesn't really matter because this is unknown, but this basis function, when it's evaluated in its proper equation, it's going to be evaluated to 0, so this is not going to affect us at all. Good. Alright, so let's look at what we have else. Well, so this thing here, this is what we want to do, so that's on that side. And then here we see that we have something that is fairly nice, because we have du dx here, which is nice because we have an approximation for u, so we can handle that. And then the derivative of v, well, those are basis functions, and we can take the derivative of them because they are known. So that's quite manageable. So we can manage this, and we can definitely manage this, and this is also known. So this whole thing is manageable. So now we look at what we end up with. If we recall that this thing here, this is this. Alright, so this whole thing that we have here is just going to be equal to our integral from up here with the force. So you can just copy this down. Right. And now we're not even interested in this part. So we're only looking at all this stuff. This is what we're looking at. And this is the important stuff as well. I mean, that this is what we can compute. So this is what we end up with. So I'm just going to copy this, put it here, and draw a square around it, or a rectangle around it. So this is what we end up with. And really, if we want to be a little bit more precise, you will see that this stuff here later, as I try to explain here, is just going to be evaluated to f, because of the boundary condition, times phi I of L. And you can verify it here because it says right here. So what we can do is just move this to the right hand side, like so. Move stuff around, and I'll tell you the reason for this. Now we have this differentiation here. I can put this as well. Yeah, so we have the approximation and the basis functions over there. And actually, I'm just hold on. Let me just fix this. I'm gonna put these guys in there as well now. So I replaced this with the Galerkin method. Okay, so yeah, so this is the complete Galerkin method for this elasticity problem now. In a nice way. We have this left-hand side here, which we'll get to soon, how we can do the details of this. But basically, we have this integral on this side, and then we have everything that has to do with the forces. These are what we call body forces, because they are in the body, and these are external forces, and both of them are on this right hand side of the equal sign. Alright, so long story short, this is how this problem is solved, and this is also what we call the weak method, the weak form. So this is the weak form of our equation, or differential system of differential equations. Yeah, so you can call this the DE. So this is the weak form of DE. And any weak form can be derived in this way. And that's in fact what we're going to look at now in this example. example 1. So I'm gonna show you an example using a general differential equation here, or well, it's not general, but it's a pretty general differential equation for a second order, or a pretty general second order differential equation here. And note that we also have this u, and I will show you how to handle that. And we have f on this side, which yeah, can be something that is quite nice, but this is dangerous to write it like this because this could be anything. So I'm just gonna make it be some polynomial here. Let's x, for instance. Otherwise, if we put sinus there, then we are in a heap of trouble, because it's quite hard to approximate that, and then this whole thing becomes nonlinear. So x, and then it's easy, or polynomial. Okay. Anyhow, we have also, just to make things a little bit more complete, I'm putting negative values in here, and yeah, we have a side condition, which is we know what u is, and we know what the differential is here. We could handle 2 of these boundary conditions, or 2 of these even, if we wanted to, but this is more natural, really. At least in terms of what this, because now we're purely into mathematics, right? And we need to sort of apply mathematical or a physical meaning to this. And these side conditions here make mechanical sense, because this is what we call a displacement boundary condition, and this is what we call a force boundary condition, because this could be a force somewhere. And here this term will be divided, and this will be called the stiffness, and this will be called the mass. So this also makes sense. There are, of course, other differential equations that have different physical meanings, but maybe not for design engineers or mechanical engineers. So we'll skip this discussion, or confine the discussion to something like this. Okay, so let's look at the recipe. So using the Galerkin method, the solution method is using Galerkin, Galerkin's method, multiply the differential equation by v, and 2, integrate by parts. Basically it's that. We multiply at least to get the weak form. So then we will have the weak form, and then 3 we can apply approximations. And once we have applied the approximation, we put everything together and solve the equation system. Solve the equation system. That's the whole method. And okay, so let's talk about why I choose to do this with v. Well, that's really called a test function, and then we can test with the various things, and usually what we're doing is we're testing with basis functions, but we could use other stuff as well, but in this course we'll just confine the discussion to basis functions. So in your head, when you see v, you just put phi there, and that's over. Good. Alright, so let's start. So first point is to look at what are our bounds. We have -1 and 2 here. So from this we know that x is in -1 and 2. Alright, so those are our integration limits. So we take the integral from -1 to 2, and we look at our differential equation here, and we sort of expand that so that we get the following. We will have minus dx of, well, u, yeah, we can do it this way, and the du dx plus u, and all of this will be multiplied by v dx. And yeah, we set this to 0, and now we can start our integration by parts. What am I saying? This is not equal to 0, this is equal to x. Alright, so now integrate by parts. So let's just use this u and v business we did up here. So we can see that, alright, let's call this our u here. This will be our u, and we have our v over here, right? That's v. Okay. So yeah, so here's another reminder how to do this. We will do dx of u and v, and that's going to be I've done this differently, du dx times v plus dv dx times u. Alright, and then maybe move stuff around so that we end up with du dx times v. That's going to be equal to u times dv dx minus d dx of u and v. So this is what we want to end up with. Okay, so now we just apply integrations around these, and we're basically there. So if you look at the first term, that's where we will be doing our integration by parts at. We have the integral -1 to 2, and then we have du dx times dv dx dx minus du dx times v from -1 to 2. So that's the so that's this business here. That's what we have now. And then we add this to it, so that's u times v, and then just integrate it. So plus the integral from -1 to 2 uv dx is equal to, and then over here, over this side, again, we take x, we multiply it by v, and then we integrate -1 to 2 dx. And this is our complete weak form for this problem. And that's our starting point to do this business. Now in the next lecture I will actually show you why we want to have all of this with integrals and why we want to do this weakly, because yeah, I think it's important for understanding to see that. So I can just mention it now that this is all of this stuff is just saying the same thing as the strong method. So it's the same. This weak form is exactly the same as the strong form here. So this is also called strong form. Because this holds pointwise. These equations hold pointwise. But these equations, they hold on average. So on average this is valid. Between -1 and 2 this is valid. But this is valid in every point in this region. So there's the difference. But if this region -1 to 2 goes down to a smaller and smaller and smaller region, and then we will hit this limit here. And what we're saying now is that we are approximating this differential equation for the whole region. But if we split our regions up, so if we, instead of going from -1 to 2 and doing this for the whole region -1 to 2, if we go from -1 to 0 and do this, and then we go from 0 to 1 and then from 1 to 2, then we will have 3 regions where our solution is much more valid. So the error that we're doing, the residual, will be less, and I will show you this soon in a graphical way instead of this, because now it's harder to see. But yeah, so that's what we're doing here, and that's also the basis for the finite element concept. Okay, so we're at this stage now. Let's look at this before we continue. So the stuff that is hiding in there is, of course, du dx at 2 times v of 2 minus du dx at -1 times v of -1. So this is contained in there, and those are our boundary values as well. Okay, so now we start with the third point, which is applying the approximations. So approximation, and we will do a second order approximation here, just because it's fun. Let's say it's arbitrary. u1 phi 1 plus u2 phi 2 plus u3 phi 3. Okay, and if you do this graphically, I'm going to show you what this means. So we are looking for these 3 points, and let's say they make up this graph here. So this is what we're looking at. We're looking at u1, u2, and u3, and they correspond to x1 and x2 and x3 on our domain. And our domain is, of course, -1 and 2, and this is going to be the middle, which is 0.5. Okay, and besides this, we have also, we know something about the boundaries. We know what u is here. So this is u of -1, and this is equal to -2. and over here we know what the du dx of 2 is, and that's minus 2. So this sort of tells us the shape of this thing. We are starting negative on this side here, and then this here is going to be is going to have a negative slope at x is equal to 2. Okay, what about basis functions? So what is phi1, phi2, and phi3 for this particular region? Well, I'm gonna show you in the next lecture how you derive basis functions for any region. So now I'm just gonna throw this at you, what this is, and I've actually computed them in Matlab here already. So those are the basis functions, and I'm just gonna write them over here. So these are basis functions for x in minus 1 and 2. And you see, I mean, you need to have basis functions for every region, so this is pretty impractical, but we'll get to how we can alleviate that problem in future lectures. Okay, so we need the derivative of u, of capital U, right? So we need du dx, and this, well, we can get this by taking the sum I is equal to 1 to n, and we take the derivative of the basis functions phi I dx multiplied by our ui here. So this is what we can do, and again, vectorized, if you prefer vectorized, because this is a vector here now, so this is a row matrix 1 by 3, and if you want to do this operation, what you could do is take the derivatives of diff dx. So I can say that, right? We take the derivative of this, so d dx of the phi vector here, and we multiply this by the row vector u. All right, so how does this multiplication look like? And this is going to be u here. How does this look like? Well, you have what this will yield is you have the phi 1 dx, the phi 2 dx, and the phi 3 dx, and this thing is multiplied by u1, u2, and u3. So you see, if you do this multiplication like so, this times that plus this times that plus this times that, you will get the same thing as you have here, but with derivatives in front of the phis, and exactly what this here says. So this is the vectorized way of doing this, and this is what I prefer. But again, you can do this however you want. I'll leave the implementation to you for this example. But I'm gonna still show you how I do it in Matlab, so don't worry about it. Alright, so that's that. So now we have handled u, we have handled phi I, and we also have d phi I dx. So you insert all of this, insert into this here, which doesn't have a equation number, so let's call that equation 1. So insert into equation 1, again for this example, right? And this will yield, which gives the following. So we will end up with the integral from -1 to 2, and then we have du dx, which is, just notice this mistake, so I'm going to correct that, du dx, and that's a scalar. So we have du dx, which is a scalar, multiplying dv dx, which is d phi dx, d phi I dx, dx, and then we have, yeah, I'm going to move that to the other side. So we have plus, we have this integral, u v, and that's just capital U times phi I dx, and then this is equal to -1 to 2 x times phi I dx, plus, because we're moving this term over, plus what we have, oh well, I'm gonna expand it now really. We have what, let's look at the boundary conditions. That's du dx of 2 is equal to -2, so du dx of 2, so that's the upper bound, right? Yeah, the upper bound, which is, if you expand it and look at it, and it's expanded here, so that is positive. So when you move it to the, we move it from here to here, this will become negative. So du dx of 2 is negative on the right hand side, and that's multiplying phi I of 2. So what is the, oh, write it out and then we can replace it. So we have du dx of 2 times phi I of 2. Important. Notice now, and this is where people make mistakes, this du dx is, it's a lowercase u here, it's not an uppercase, so we don't replace this with a approximation. We could do that, but that would be a completely different method. This is given, so this thing here evaluates already, this is given by the boundary conditions, and this is -2. So this thing is really -2, but since you're moving it to this side, this is actually negative. So there's a minus sign there. So this is -2. So this becomes positive. Yeah, and then you just have to evaluate the basis functions at 2 here, and that's it. So this is what we end up with. Okay. Now the rest of this is enough stuff by hand. The rest we will do now in Matlab. So I'm gonna switch back to Matlab now. Alright, so back in Matlab, I start by defining the basis functions. So as you can see here, the basis functions are given by these values over here, and this is only valid for this range -1 to 2. And again, in the next video, I'm going to show you how to derive these basis functions and what properties they will have. But just to make sure that I have typed this in correctly, I will evaluate phi, the basis functions, at -1, and they should produce this, which is 1 in the first basis function and 0 for all others. And then I'll do 0.5, and then 0 for the first, 1 for the middle one, and 0 for the last, and again 2, and I should get 0 for the first 2 and 1 in the last. So this is just a sanity check to make sure that this produces the correct results. So I can show this transpose like this, it's just easier to read. Alright, so now what I want to do is I want to actually put the weak form in here in a proper way. And I can show you how to do this as well, because it's quite nice to use this MATLAB LiveScript as a report writing tool. And you can insert equations by going to the insert tab and going to equation here, and you can have this equation typed in, or you can even do LaTeX equations if you want. But this editor also handles LaTeX symbols, so you can choose everything from this screen here if you want, and after a while you will just learn the LaTeX commands. And LaTeX it's not just used in sorry, LaTeX is not just used in MATLAB. It's a typesetting language which is very general and used in all sorts of report writings, from mathematicians to physicians and chemists. And you should really, if your reports are mathematically heavy, you should definitely consider using LaTeX editor. And I will actually do a video on how to use one at a later stage. So we will type in this this weak form now in MATLAB. So I'm going to use the short commands: int def here, going from -1, and I'm doing tab here to switch between these, -1 to 2, and we're doing du divided by dx, and then d var phi over dx, and then dx. So that's the first integral, and then we add another integral to this. And I can now copy all of this in here. That works as well, left to right. I replace this first term with u, and then this other one here with var phi. So there's that, plus I insert another integral, get rid of this, but it's not plus, it's equal to, and then we have this x term times phi, var phi. Yeah, and then all of these are really indexed, so it's var phi I, and also here, because there's going to be 3 of these guys. Put that in the wrong place. There we go. Like so. And then we have, let me just remind myself here. Yeah, so if we move this term to that side and expand it, what will we get? We will get plus, and I'm going to do a parenthesis here, and then we have du, putting spaces between these now, of the upper bound, which is 2, times var phi 2, and then minus the lower bound. And I'm going to copy this in here and do -1 and -1 here as well. So this is the weak form, right? The weak form is given by there. Now what I want to do is I want to also paste in a small drawing showing these nodes on the x-axis, right? Because we are going to look for these unknowns, and some of them are unknown, but some of them are really not unknown. So I'm gonna go ahead and do let's see here, I'm gonna take this stuff, or maybe I already did copy it in here. Yeah, I did. So let's do it. Let's cancel and go back. The weak form is given by this, and the strong form is, I'm doing this in the wrong order, but yeah. So this is also equations written in Matlab I did. But what I want to show you is the following now. this is good to have a clear picture in Matlab what's happening. And then this drawing here tells you, all right, so you have 3 nodes, right? Because it's the approximation that we're going to use is going to be quadratic. And we can, in the first and last, so what I could have done here is also write in that this is -1, this is 1/2, and this is 2. So what is known and what is unknown here? So I wrote parentheses around du2. So these are the differentials, right? Du dx. And this middle one doesn't really exist. There's no differential that makes sense in the middle node. But for the others, there is. I mean, yeah, sure, you can have a middle node one, but it's really not useful. You can have infinite many if you want. You just differentiate the approximation, you get all of them everywhere. But at the borders, that's where these are useful. And what is given here is this one. So we have a value for the udx 2. That's actually -2. So this value is known. This is unknown, but this one is known. That's 1. And then these guys are unknown. So if we just look at how many equations will we have, well, we're going to have 3 of them, because we have 3 basis functions, and then these basis functions are directly tied to our unknowns. But we are also going to have, this is not going to be an unknown, we're going to have u2, that's 1, u3, that's 2, and we're going to have du1, that's 3. So we're going to have 3 unknowns and 2 knowns in here as well. So we need to handle that. And the first thing I'm going to do here is actually solve this strong form using a differential equation solver, which is included in Matlab in the symbolic toolbox. So yeah, so I'm going to show you how to do that now. First, before doing anything else. So I'm going to create a UE of x, and this UE is representing the exact solution, so U exact. And additionally, I'm going to create a differential equation by doing differentiation of this UE. So I can do this in several ways. So basically what we have here is du dx 2 times. So I can do diff and then diff again, for instance. So I can do this, and then with respect to x, and yeah, basically that's it. So if I do this now, it's going to give me this. So Matlab does partial differentiation, so d2 dx squared of this. And of course I can get rid of this here, and really tell it how many times I want this to be differentiated. So if I do 1 here, it's going to do it 1 time. If I do 2, it's going to do it 2 times. And that's a little bit cleaner, and I actually prefer this. So we have that, and then we have u here, so that's ue, and that's going to be equal to 2 equal signs x. So that's my differential equation. Good, I don't need to see that. Now I'm going to create the differential, which is du of x, and that's just diff ue with respect to x. And I need this in a second here. So now I can create my boundary conditions, and the first boundary condition is this one here. So ue of -1 is going to be equal to 1. That's my first condition. And then I have another condition, and that's why I created du of x here, because du of 2 is going to be -2. -2. So this is what I want to do. So ue of -1 is equal to 1. That's correct. But then it changes notation here, and that's because it can't really handle du of 2. So it does this instead, which means the same thing. So du dx of ue of x evaluated, that's what this line means, at x is equal to 2. So it's exactly the same thing, and that's equal to -2. Alright, so that's my boundary conditions. And now I can just send this off, the differential equation and the boundary conditions, I can send off to the differential equation solver. And I want ue to be returned. So I do ue is equal to dsolve, that's the differential equation solver, and it takes equations, which is my differential equation, and the conditions are going to be B, C. And I don't have any options. I'm just gonna run this, and this is what it returns. It returns this thing, which is an exponential equation. All right, so now I have an exponential equation, and I can plot this. So I'm gonna go ahead and do figure, and I'm going to f plot, and UE, and the interval is -1 to 2, and I want this to be red, so I just do like this, short command, and this is my equation. This is the true solution for my equation. Now if I create the Galerkin solver, I can compare it to this, and I can actually fiddle around with the numbers here and quickly test out different equations. So that's my true solution. So I can just write it here, true solution. Solution, or exact, perhaps, exact solution for the differential equation. All right, now I switch to the approximation. Okay, so what do I need to do? Well, I need to create a bunch of symbolic variables. Sims, I need u1, u2, u3. I need my du1 and du3. du1, du3. Like so, and I want all of these to be real numbers. Okay. For my basis functions, I already have it here. So this is phi, that's correct. I did a quick test, it works. Now, how am I going to approximate u? Because I need to do the following. I need to do this approximation here. So u is approximated by just multiplying these u's with the basis functions. And I can do that in different ways. I'm going to show you how I prefer it, which is to do phi and then multiply this by another vector, which is u1, u2, and u3. u1, u2, and u3 here. And this will yield a scalar, and this scalar I called capital U, like so. Okay, and I can actually, in my workspace, I can view that this is a sim function now. So I can actually evaluate this for x if I want to, which I'll be doing later. Alright, so what now? How about du? So du, I can actually just take the differential out of this. So I can do diff u and with respect to x, and basically I'm done. That's one way of doing it. But I will be needing the differential equation, the differential for phi as well. So I can do d phi is equal to diff phi with respect to x. So this is it. And now I can go ahead and do du by just taking the d phi and multiplying it with my u's again, this way. And this should yield the same solution. And if it doesn't look correct, oh, that's because I don't do it correctly. Yeah. So if I want, I can do simplify the u here, and it is already simplified. All right. So, but yeah, I can go ahead and do this just to try it out. I can do diff, take the derivative of u, and simplify it, and well, it should be the same as this, perhaps. Expand du. Yeah, there we go. That was just expanded, but it's the same solution, as you can see. All right. So I have u, I have d phi, I have du. I have all of the stuff I need to create my weak form here. So the way I'm going to do it now is in steps. So I'm going to go ahead and do the first integral, I1. I'm going to do int, and what I have here, I have du dx, so that's du here. Go grab that, du, times, I have d phi, and this is integrated with respect to x from -1 to 2. Run that, and this is the resulting integral here. Okay, let me just go ahead and transpose this as well, so I can see it more clearly. Okay, now I2 is going to be int what? Well, u. So I have u times phi with respect to x from -1 to 2. And again, let me transpose that to see it more clearly, like that. Good. Then I have the right hand side of first integral, which is I3 int. I'm doing x times phi with respect to x from -1 to 2. And now for the final term, we have to be careful here. So what we have is, we call it IB, and what do we have here? We have du dx of 2, right? And that's this one here. So this is what we call du3. So we have du3 times phi evaluated at the x is equal to 2. And we take minus, so this is the upper term, minus the lower bound, which is du1 times phi evaluated at -1. So we run that and we see here that, okay, this is what we have, all right, makes sense. Transpose that. Let's put it and transpose it like so. Good. Now our equations, EQX or EQS is equal to, we have I1 plus I2 plus I3, no, is equal to I3 plus IB. So this is our final differential system or approximation, and what we will do now is to substitute. So basically we're saying that, all right, we know what u1 is. U1 is what? It's 1. And we know what du3 is. That's -2. And then we just do EQS is equal to subs EQS. So this is before substitution and this is after substitution. So now how many unknowns do we have? u2, u3, and du1. Those are unknowns, and this is what we're going to solve for. 3 unknowns, three equations. And guys, remember, if you're just solving for u1, u2, and u3, that's going to be completely wrong, because you're not taking you're not handling the boundary conditions, and your solution will be completely different from the true solution. So this is what you need to do. All right, so how do we solve this? Well, the way we did it before. So just throw it into solve. So we have u2 and u3, and we have du1 equal to solve, and we're solving EQS, and we are giving it these variables in this order because this is how we want them back. So these are return values, and now we can just substitute these into u. So we can do u is equal to substitute u. And let's do simplification as well. Simplify that thing, and this is what we end up with. Right, and if you want, you could also do VPA on this now to make it into a numeric value with 4 significant numbers, like so. Good. Now let's plot this. Actually, I'm gonna go ahead and back up here because I don't want to have it in VPA form. Yeah. So now we can actually try something. We can try if this is going to give us back minus or 1, and it does. Very good. Now take care, because this is not going to work. Diff u with respect to x, and then evaluated at, so you can call that the u, and this evaluated at 2 is not going to produce minus 2 exactly, and the reason for that is that this is an approximation. It's not going to be very strict. And let's view the plot here. So we can do hold on and fplot u in the same range, -1 to 2, and with the color blue, and see what we get. So see, it is correct in this point, and then the slope of this is not really the same as this. But then again, if this slope were the same, then because this is a second order equation, the error will be much higher. So that's why the slope is modified. It's not strict. It's not strictly the stuff we have inserted. It's modified a little bit to make the overall error, the overall area, be as small as possible for the given boundary conditions. That's beautiful. And what we can do is actually we can compute this area now, right? We can do, because you have UE and you have U, so you can do U minus UE, for instance. You can take that difference and you can integrate this difference. So you can do int and take this difference for x from 0 to 1, -1 to 2. And then we can do VPA on this. And this is the actual integral. So we can see, of course, that we have some error. So it's not completely, it's not going to be completely 0. These guys here, but it's as small as it can get for this particular approximation. And yeah, so that's the best fit. This thing here is the actual integral, but we can do something else. We can do what we call what is called L2, and that's the error. And this error is defined as the square root of the integral from a to b, and you take the true solution minus the approximate solution and you square them. Dx. So this integral, if you compute this, then this is a standard measure of error. And because we're measuring this way, that's like on average error. So we can do this as well, and that just looks a little bit different from what we had here. So it's basically this, it's just that we need to square this as well. We square this and then take square root out of this, and this can be done by just to the power of 0.5 and VPA. Let's do 4. Yeah, so this is the L2 error for this particular problem now.